Hi, class. Excuse me. Hoping that's not Coronachem virus. Not feeling sick. So I'm going to start today by showing you how to draw the bonding in acetylene, to show you how the overlap of bonds results in two types of bonds, the sigma bonds and the pi bonds. Now, in a typical sigma bond, say for example with methane, the orbitals are hybridized so that you get sp3 orbitals, 4 sp3 orbitals, and then the hydrogen atoms overlap with their s orbitals. So that orbital overlap is a sigma bond. Okay, that's a Greek letter sigma. And there's 4 of them, obviously. And these orbitals are generated by combining 1s and 3p orbitals to form 4 sp3 orbitals. But what happens when you get double bonds and triple bonds? What kind of arrangement is taking place? Well, let's take the example of ethene. Ethene is this molecule. So it's got 3 bonds that are equivalent in the carbon atom. This carbon atom is sp2 hybridized, so it's composed of 1 s orbital and 2 p orbitals to give you 3 sp2 orbitals. And the hybrid orbitals are oriented in such a way that they form 120-degree angles roughly. And so you get the hydrogen atoms overlapping here. But what happens with the 2 carbon atoms? The 2 carbon atoms, there is a sigma bond, so that's a sigma bond here. But then, and of course the other orbitals are there. These are all sp2. This is sp2. This is an sp2 hybrid. This is an sp2 hybrid. So is this. What happens to create the second bond between the carbon atoms? Well, what happens is you have the other p orbitals that are still unhybridized just sitting there. And because these orbitals are very fat, they actually overlap sideways. They create a high electron density in that area above and below the plane of the sp2 bond. So each one of these, it constitutes half of a pi bond. So 2 of these together equals a pi bond. So what we observe as a double bond is composed of a sigma bond and 1 pi bond. What would happen in the case of acetylene? It has 3 bonds holding it. Acetylene is a C triple bond C molecule. So it looks like this. If you were to show the hybridization, this carbon atom is a combination of 1 s and 1 p orbital to give you 2 sp orbitals. One pointing this way, one pointing that way. So that creates 1 sigma bond between the 2 carbon atoms. So you could show that. There's the sigma overlap. So this is an sp orbital, this is an sp hybrid, it's an sp hybrid, that's an sp hybrid. And there are now 2 p orbitals that are not hybridized. They're still sitting there, 1 above and below, and 1 coming out at you, and 1 going behind the plane of the blackboard. 1 above and below, 1 coming out, and I'll have to erase this to see, and 1 going behind. So what happens is the 1 above and below form an interaction. So that's a pi bond. That's a pi bond. and the ones that come forward interact, and the ones that go behind are interacted. So that's also pi bonds. So 2 of these equals 1 bond. All right, so because you have 4, you get 2 pi bonds and a sigma bond. So the triple bond between carbon atoms in acetylene is constituted by 2 pi bonds and a sigma bond. One of them is the result of a hybrid. The other 2 are the result of sideways overlap of the p orbitals to form a pi bond. If we go to page 370, from what we've reviewed before, we can tell what the bond angles are going to be within the molecules. When you have an sp3 hybrid, like I said earlier, it was yesterday, the bond angles are going to be 109.5. If you have an sp2 hybrid, the bond angles are 120. Sp hybridized gives you bond angles of 180, and of course you get some distortion if some of those orbitals have lone pairs. When you have lone pairs, they tend to push the bonding pairs down, so it decreases the bond angles from what you would expect. On page 370, the practice exercise asks, consider the acetonitrile molecule, predict the bond angles around each carbon atom, and B, describe the hybridization at each of the carbon atoms. C, determine the total number of sigma and pi bonds in the molecule. So let's draw acetonitrile. It's got triple bond to N, then another bond to carbon, and it's got 4 hydrogens, or 3 hydrogens. So this has got 4 bonds, so clearly it has to be sp3 hybridized, and therefore the bond angles here are 109.5. This has 2 bonds available on either side. Remember, these are pi bonds. This is the sigma bond. So because there's 2 sigma bonds, one on one side, one on the other, this has to be sp hybridized, and of course the bond angle here is 180. So all of these are 109.5. And this one is also 180, it's 180 with that one. One of the interesting things about pi bonds is they're not quite as strong as sigma bonds, and because of that, when you expose the molecule to things like light or even higher energies, like when you boil a solution, it can create delocalization of those electrons. If you add enough energy to those pi electrons, they can flip, and it happens in benzene, for example. Whenever you have alternating single and double bonds, you can create the conditions where you have delocalization of the electrons. So for example, in benzene, which has alternating single and double bonds, the pi bonds can move around. So you can get multiple resonance structures, and that's called resonance stabilization. It makes the electrons less available for reaction. And in the case of benzene, because it occurs in a particularly stable arrangement, we call that aromaticity. So benzene has special properties. It's relatively unreactive because of the unavailability of those pi electrons. Normally, double bonds are fairly highly reactive sites, but because of that resonance stabilization, they're less available. On page 371, they ask you to comment on molecules which have delocalized bonding. So for example, sulfur trioxide, sulfite, formaldehyde, it looks like, and ozone, and ammonium. So it says, which of the following molecules or ions
will exhibit delocalized bonding. Well, let's have a look at all of them, one at a time, of course, or maybe two at a time, because we don't have that much room on the board. If we look at sulfur trioxide, if we draw the Lewis structure for sulfur trioxide, we've got 6 valence electrons on sulfur, 6 on oxygen times 3, so there's 24 electrons to account for in the structure. When you draw it out, what you get is this. Okay, so there's not a lot of need for delocalization because each of the atoms has an octet and it doesn't have any what sulfur trioxide can do is it can actually have the electrons go onto the oxygen, and what would happen is you would have a formal charge of -1 on the oxygen and a formal charge of +1 on the sulfur, and all the other ones could also do the same thing. So there is the availability of delocalization in this molecule. All the other ones could do the same thing. With sulfite, which has a -2 charge, you would have to add 2 more electrons. So now I would have 26 electrons. If you were to disperse all the valence electrons, you get 6 times 3 is 18, 20, 22, 24, 26. And drawn this way, you would have a plus charge on sulfur and a negative charge on each of the oxygen atoms. You could probably reduce it a little bit by adding, by sharing one of the lone pairs, and you would get this. So it still has a -2 charge overall, and what you really have is 4 bonds being shared equally over 3 positions. There is resonance stabilization in the sulfite as well. If you look at formaldehyde, it'll look like this, and there's not much delocalization available there. If you look at ozone, let's make room for the ozone. Ozone is peculiar in the sense that it actually relies on delocalization to maintain its stability. So it's not a very stable molecule, in fact. It's quite reactive. There are 6 valence electrons in oxygen, and there are 3 oxygen atoms, so you're looking at 18 electrons. So if you draw your atoms in a straight line, we can worry about the geometry after. If you disperse the remaining electrons, you have 2, 4, 6, 8, 10, 12, 14, 16. Wait a minute. I put too many. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay. So if you draw it this way, you're going to have a negative charge on this one. This will have an octet, which is fine, 2, 4, 6, 8. This doesn't have an octet, and on top of that, it doesn't have full possession of 6 electrons. It's only got possession of 5. 2, 4 plus 1 gives you 5. So you got a negative charge on one side and a positive charge on the other. That's not the ideal way to draw that. So one of the resonance stabilizations possible would be, as opposed to share this lone pair, which would give us this. There would still be a positive charge on there, and it would have it would still have the octetal 2, 4, 6, 8. But this one would have a positive charge. That would have a negative charge, and then you could also have it go to another resonance structure where you would have this lone pair go in there, which would cause this one to go back up here, and then they would alternate between this and the other one. So this would look like that. This would still have a plus charge. Now this one would be the one with the negative charge. So these are probably the principal resonance structures. Of course, this is also a possibility, probably a minor form. Point is, the molecule can exist, but it's not super stable and it's quite reactive, and you can see why, because there's no real comfortable structure that you can draw for it, where all the formal charges are properly dealt with. And if you so there's multiple there's multiple resonance structures available that allow the delocalization of the electrons, so that they can all share the burden of keeping the electrons. It's kind of like they're playing hot potato. And with ammonium, you don't have a lot of choice. It's going to look like this. It's got a plus charge on the nitrogen, and you got the 4 hydrogen atoms. So there's no real resonance. You can't draw alternate structures for ammonium. So it doesn't have any resonance stabilization. So the two that have it in abundance are the sulfur trioxide and the ozone. Now I'm going to recommend the video because I just discovered today that this is the only thing I don't have a video for. So I'm going to recommend somebody else's video for you to watch, just to give you some background on molecular orbital theory. It's in chapter 9 of your textbook if you haven't already read it. As far as I'm concerned, this is still essentially a review. But watch this video. It's not going to be mine. It's on YouTube. And it's called Molecular Orbital Theory versus valence bond. Okay, and it's by Dr. Jackson of the UGA. And that says Ken, and I didn't see the rest of the title. But if you enter this in YouTube, you'll get the video. Okay. This part of the chapter basically talks about how bonds can form within molecules, but you look at the whole molecule, not just the valence shells. And what you do is you account for all the electrons that are present in the atoms that are involved in the bonding. And you can either get constructive interference between the waveform of the electrons or destructive interference. So if you get constructive interference, the waveforms will overlap and you get a bond forming. If you get destructive interference between the waveforms, the molecules, the atoms will repel each other because the electrons actually are in space at the wrong time. They end up repelling each other. So the interplay of the waveforms of two atoms which are about to form a bond is such that in some cases, on the average, you do get a bond, and in some other cases, on the average, you don't get a bond. So for example, if you're dealing with hydrogen, you get a bond. So two hydrogen atoms, when they meet in space, will form a bond because their waveforms will overlap effectively and create a connection between the two atoms. If you try to do that with helium atoms, won't work. You will not get bond formation, although under certain conditions, helium atoms can interact so that they form a certain amount of bonding. You have to raise the temperature to a very high level. I think with lithium, you can get the same thing. You can get a dilithium molecule. So, as it turns out, Star Trek wasn't completely fantasizing. Let's do an example together on page 375. First of all, I'll just give you a little formula. For molecular orbitals, the bond order is equal to 1/2 bonding electrons minus the antibonding. And there's an example on page 930, figure 937. This is on page 376 of your textbook. I'll draw it out for you so you see what it's all about. So what you do when you do a molecular orbital diagram is you diagram both of the atoms, one on one side, one on the, hi Timmy, one on one side, one on the other. Okay, so here's the energy of the atoms, and here's one lithium atom, here's the other lithium atom. Say you were trying to calculate the bond between, for a dilithium molecule, if such a thing is possible. And you have to account for all the orbitals in the first molecule and all the electrons in the second molecule. So the first molecule is going to have the 1s2 orbital. It's going to be filled with electrons, and so will this one. It's going to have two of them in there. So they're going to be one there, one up, one down. So because they're in the same orbital, the electrons are portrayed as an arrow going up and arrow going down to show that they have different spins. They can't be occupying the same orbital if they have the same spin. Now, these two orbitals have 4 electrons available, so it generates 2 possibilities at different energy levels. So let's draw those 2 possibilities. You could have a bonding orbital, which is a lower energy, or you can have an anti-bonding orbital. If you have 4 electrons available, the bonding and the anti-bonding will fill up. So we label these sigma. So we'll call these sigma 1s and sigma star. If you put a star on it, it means it's anti-bonding. Okay? That uses up the 4 electrons that are in the s orbital at the first level. Now let's go to the second level, which is where the 2s orbitals are. Remember that lithium's configuration is 1s2, 2s1. Okay, so it's only each one has only 3 electrons. So here's the 2s1 orbital. And 2 possibilities arise here as well, bonding and anti-bonding. But there's only 2 electrons available. So what's going to happen is you're going to have one up and one down in the bonding orbital. The anti-bonding orbital is going to remain. So this is going to be the sigma 2s, and the sigma star 2s is going to remain empty. So under conditions, under what conditions will this happen? Let me read about that. So when lithium is heated above its boiling point of 1,342 degrees Celsius, dilithium molecules
are found in the vapor phase. The Lewis structure for lithium-2, dilithium, indicates an Li-Li single bond. So how does this happen? Well, if you use the molecular orbital explanation, this is what you come up with. You get a bonding orbital. Remember that it's the bonds are determined by the number of bonding minus antibonding divided by 1/2. So how many bonding orbitals are there? 2, 4. How many antibonding? 2. So 4 minus 2 gives you 2. Divide that by 1/2. So you have a half a bond. That's a half. Sorry, not half. You got one bond. You got one bond. Because 2 divided by 1 by 1/2. 2 divided by 2 gives you 1, or 2 times 1/2 gives you 1. So if you
Plug that into the formula, bond order is equal to 1/2 bonding minus antibonding. It'll be equal to 1/2 times 4 minus 2 in this case, which gives you 1.
So what you can try tonight, if you have your textbook with you, is just to continue reviewing 937. Take a look at it, try to read up to there again, and then do a homework on number 921.
Just brush up on your vector theory.
Okay? And we'll talk tomorrow. Hopefully the internet doesn't go dark, because I've been hearing some interesting rumors about people being arrested, large numbers of people being arrested. May it be good, may it be true. It would be nice if our Western world changes for the better. We'll see you tomorrow.